Okay, hello everyone. I hope you guys are doing great. So today I'll be discussing the solutions to code process round 842. This round ended an hour ago, right? So we'll be discussing the solutions to the first five problems today. And before that, talking about the round, I would say that this was a fairly good round. Not the best, but not very bad as well, right? So I really liked problem B, although it is easily solvable through guessing, and I'm sure a lot of people must have guessed it. But still, I really liked the sense of the problem. C was a bit weird for me because it required some weird implementation stuff, and like thinking about the solution was not that difficult for C, right? And also, problem D was a bit too standard, I would say. Like reducing the number of permutations, reducing the number of inversions in a permutation is a very standard problem, I would say. And talking about E, although the number of solves are quite less for E, I would say that E was typically easier than a normal division 2 problem E. I think a number of people just gave up after solving D because if people did attempt this problem seriously, then I don't think it's that hard, right? So yeah, that's my analysis of the round. So with that, let's start with the solutions. So let's start with problem A. Okay, so in this problem, we have an integer k, and we need to find an integer x which is strictly smaller than a, such that this expression x factorial plus x minus 1 factorial, this is a multiple of k. And if it exists, we need to output it. Otherwise, we need to determine that no such x exists, right? So yeah, this is the problem. Let's see how we can solve this. So this is like really easy. So if we analyze this expression, the expression is x factorial plus x minus 1 factorial, right? Yeah, so that is the expression. So what we know here is that x factorial is nothing but x minus 1 factorial multiplied by x, right? So we can write this as x minus 1 factorial into x plus x minus 1 factorial, which further simplifies to x minus 1 factorial multiplied by 1 plus x, right? So if we substitute x equals to k minus 1 here, what will we get? We'll get k minus 2 factorial. So we'll get k minus 2 factorial multiplied by k. And as you can see, this is always a multiple of k, right? So here's the solution. You can simply output k minus 1, which will be your answer, right? So yeah, the answer will always exist and it will be k minus 1. So that's the solution to this problem. Pretty easy, I would say. Now let's move on to the second problem, problem B. All right. Okay, so this is a really nice problem. I think this is a very good example of how a division 2 problem B should be, right? So the solution is not very obvious once you read the problem, but if you think for 2 minutes, it will hit you. So that's the kind of problem that a div 2b should always be. So we have a permutation of length n, and we also have an integer k smaller than or equal to n. Now we can, as always, perform certain operations on the permutation. And in one operation, what we can do is we can choose some k distinct elements, and then we can remove these elements, and then we can put them to the end of the permutation in a sorted fashion, right? So this is what we are allowed to do. Now our task is to find out the minimum number of operations we need to sort the permutation in increasing order. And yeah, so that's the problem. Okay. It can be proven that it is always possible to do so. It's fairly obvious. You just keep taking the suffix of length k, the prefix of length k, and keep performing the operation, and you'll get a sorted version, right? Cool. So yeah, we need to find the minimum number of operations, right? So that's the problem. Now let's have a look at the solution. So the solution is simply based on one observation, and that observation is also not very obvious once you read the problem, but if you think for 2 minutes, it will hit you for sure. So here's the solution. So there is just one main observation, right? So the observation is that if we look at the subset of indices, the subset of elements on which we perform at least one operations, right? Then that subset will form a suffix of the numbers from 1 to n. That's what I'm trying to say. So let's write it down. So the numbers So the subset of numbers, or maybe the sequence of numbers. Let's just keep it subset. So the subset of numbers which are on which we perform at least one operations, on which we perform at least one operation will form a suffix of 1, 2, 3 up till n. That's what I'm trying to say. So if we perform three operations, if we perform an operation on three numbers, then those three numbers are going to be n minus 2, n minus 1, n. This is what my claim is, right? Now, how can we prove this? So I think this is something which was guessable in the contest, but let's see how we can prove this, right? So here we go. All right. So let's say we have two numbers I and j. Initially, I is to the left of j, right? This is I and this is j. And we know that I is smaller than j, right? So initially here is I and here is j. Now what we want to do is we want to do an operation on I. And what I'll prove is that if we do an operation on I, just a moment. Yeah. So what I'll prove is that if we move I, then we will also have to move j. This is what we'll prove. And if we prove this, then it'll be sure that if we look at the subset of elements that we are moving, then they will form a suffix, right? So now let's consider we have I and j such that j is greater than I. Now I'm saying that if I'm moving I, so let's just write down for I less than j. If we move I, we'll also have to move j. So what happens when we move I? So the moment we move I along with some other numbers, definitely we'll choose k numbers, and let's say one of those k numbers is I, right? So at that instant, I will be removed from here and it will be put somewhere to the end of the sequence, right? Meanwhile, j is not being touched. So that means that I will be always to the right of j once we move it, right? And now in the sorted permutation, we obviously want I to be to the left of j. And for that, we'll also have to move j, right? So yeah, this is the proof. If we move I, then I goes to the right of j. And in the final sorted permutation, we want it to be to the left of j, right? So that is why we'll have to move j as well. So the problem simply boils down to finding the smallest prefix, finding the smallest suffix that we will move. If we can find the length of the smallest suffix that we'll move, then we can just divide it by k and take the ceiling, and that will be our answer because we'll just keep moving k elements at a time, right? So if I decide to move elements from I plus 1, I plus 2 up till n, then what I'll do is I'll first take the smallest k, then I'll take the next smallest k, and so on. And that will make sure that all these elements are actually in the sorted order in the final array, right? So if we want to find the smallest prefix, we want the largest suffix which we do not move. Sorry, largest prefix which we do not move, right? And the largest prefix which we will not move will be just 1, 2, 3 up till ni, right? And we want the largest such value of I. So what we want is we want the size or the length of the largest subsequence which starts from 1. And if the subsequence is represented by xi, then we'll say that xi is equal to xi minus 1 plus 1, right? So essentially what I'm trying to say is we want to find the largest subsequence of the form 1, 2, 3 up till I, which is present in the permutation. Because if we keep all these elements stationary, then we can just move all the other elements and they will come to the right of I, right? So that's the simple problem that we have. And finding it is not very easy. You start with 1 and then you look for 2, then you look for 3 to the right of 2, then you look for 4 to the right of 3. If you find 4, then you increment your answer, right? So that's the basic algorithm. So yeah, that's pretty much it. That's the solution to this problem. Let's just have a quick look at the code. So the code is pretty simple. What you're trying to do is you're trying to find the value of this number cur, right? So you're trying to find this number cur. If you find this number, then you just increment cur. So initially I want to find 1. As soon as I find 1, I'll start looking for 2, right? If I find it, I will increment my answer, which is count. So if there are count numbers which I'm not moving, then there are n minus count numbers which I am moving. So I'll just divide that by k and take the ceiling, and that will be my answer, right? Cool. So yeah, this completes the solution to problem B. Let's move on to the third problem now. Okay. So in this problem, we have an array of n integers, and what we need to do is we need to find two permutations p and q of length n, such that for all I, maximum of pi and qi is equal to ai. That's going to be our target, and this is it. This is the problem statement that we have, right? And if it is possible, we need to find these two permutations. Otherwise, we need to tell that it is not possible, right? Cool. So yeah, this is the problem. Let's have a look at the solution now. Okay, so let's start this problem with a trivial observation. Okay, so for every I, since max of pi and qi is equal to ai, either pi is equal to ai, either pi is equal to ai or qi is equal to ai, right? So this is going to be true, right? So that means that the count of any number in the original sequence A, it can't exceed 2. So count of I is less than equal to 2 for all I in the array A. Now, why is this true? So this is true because if count of I becomes 3 now, then something like this will happen, right? Let's say the number I occurs here, here, and here in the array A, right? So let's look at what happens to P and Q. So in this index, either P or Q will have an I, right? Now in this index, either P or Q will have an I. P can't have an I because we want P to be a permutation, so we are forced to put Q as I. And in this position again, we need an I, right? But if we put an I here, then this won't be a permutation. And same goes for if we put an I here, right? So this is not possible, and this is not possible. So with this, we have proved that count of I will be smaller than or equal to 2 for all I. So if count of I is greater than 3 for any is greater than 2 for any number, then we strictly output no, right? Okay, cool. All right. So now let's move on. I don't think this observation will even be used in the final solution, but it's actually a good observation to do. Cool. So now let's look at the solution. How will we actually solve this problem? So for that, let's look at the number n. So let's look at n, right? So what happens if we have two n's in the array A? I claim that if we have two n's in the array A, then again the solution, no, then the solution can exist. So there are three cases. The number of n's is 0, the number of n's is 1, or the number of n's is 2, right? So let's look at what happens when count of n is equal to 0. Okay, cool. So one thing that you need to realize is that if count of n is equal to 0, then answer will never exist. The reason is that p and q are permutations. So p and q are permutations. So they will have n somewhere, right? And if they will have n somewhere, so let's say pi is equal to n, then we are sure then max of pi and qi will also be n, right? Because they are permutations of length n, so an element in it cannot exceed n. So we know that max of pi and qi is equal to n, meaning ai is equal to n. So that means that we should have at least one occurrence of n in the array, right? Cool. So now let's look at what happens when count of n is equal to 1. Okay, so if count of n is equal to 1, as you can see from the first case, in whichever index we put n in the first permutation and in the index we put n in the second permutation, both of them will have n in the array A, right? So what I'm trying to say is that if we have these two permutations, P and Q, right? So let's say this index is n in P and this index is n in Q. Then in the final array A also both of them will be n only because maximum can never exceed n, right? So that means if count of n is equal to 1, both of them have n at the same index, right? So what we can do is put n in both permutations at the specified position. The specified position is the position of n in the array A, that is pos of n in A, and solve the problem for 1 to n minus 1, right? So this is what we can do. So this is a pretty easy case. But now let's see what happens when count of n is equal to 2. Okay, so count of n is now equal to 2. So now if count of n is equal to 2, I don't think I need to explain much. What happens is that we have P, we have Q. So let's say in A we have two n's, one n is here and the other n is here, right? So in this case, in these two positions, one of them will have n here and one of them will have n here. It doesn't matter. It doesn't really matter in which permutation we put n there, right? So we'll put n's here, and yeah, this will be it, right? Okay, so now what happens is that once we do this, let's look at these two positions, this position in Q and this position in P. So these positions are now empty positions, and so let me write it down. So we generate two empty positions, one in P1 and one in P2. And notice that whichever number we put here in these two empty positions, it doesn't really matter because the final number in A would still be n because these numbers can never exceed n, right? So maximum of them will always be n. So we just have two empty positions which we can use later on, right? Cool. So now what happens is now we'll solve the problem for n minus 1. And now if count of n minus 1 is equal to 0, it is not necessary that answer doesn't exist because we have these two empty locations, right? And we can use these two empty locations to put the number n minus 1 there. So we can just keep doing this, keep track of the number of empty positions that we have. And if count of a number is equal to 0, then we will have to put we'll have to put the number in both P1 and P2 in some empty position if we have an empty position, right? And if count is equal to 1, then we'll have to put both of them in the same place. And if count is equal to 2, then we'll have to put both of them in different places. But at the same time, we'll generate two extra empty spaces, one for P1 and one for P2, right? So with this general scheme of algorithm, we can implement this solution to this problem. So let's just have a look at the code. Okay, cool. So what I'm doing is in this ADJ matrix, I am putting the locations of all the elements, right? So, and also I'm keeping two stacks. I think there can be other ways to implement this, but this is what I did. So one stack keeps track of all the empty spaces in A and the other keeps track of all the empty spaces in B. Okay. So now I iterate from n to 0. This extra variable denotes the count of the number I, right? Now, if count is equal to 0, what that means is that we'll have to look for one empty space in A and one empty space in B, and we'll have to utilize that space. So if empty spaces of A is empty or B is empty, then the answer will be no. So we can just break out. Otherwise, there are two positions. The first position is going to be an empty space in A. So we'll just put I there in P1, and then we'll have an empty space in B, and we'll put I there in P2. Okay. Okay. Otherwise, if the count is 1, the count of an element is 1, then we'll just have to put that occurrence of the element in the specified position. Right. The last case is that count is equal to 2. So if count is equal to 2, then we'll just put them in those positions. So this is what we are doing here. And also two empty spaces will be generated. So we'll just push these empty spaces into the stack. Notice that here we are also popping the empty spaces as and when we are using them. So that is the use case of a stack here. Finally, if the count is greater than 2, then I'll simply break out, right? So if I'm okay, then I'll just output P1 and P2. So yeah, that's the solution to this problem. Hope this was clear enough, right? Cool. Okay. Now let's move on to problem D, right? Cool. So here we have a permutation again. So this round is filled with permutations. I think problem E is also permutation, right? So four problems, all of them based on permutations. Wow. Anyways, so we have a permutation of length n. And what we do is in one operation, we choose two indices and we swap pi and pj. This is what we are allowed to do. Now our task is to find the minimum number of operations which are needed to have exactly one inversion in the permutation. So for those who are not familiar with the term, an inversion is basically the number of pair of indices ij in the array, such that I is smaller than j, but pi is greater than pj. Right? So yeah, that is an inversion. So what we need to do is we need to find out the minimum number of swaps that we need to do so that we can reduce or increase the number of inversions in the array to one. Okay, cool. So let's see how we can solve this problem. Cool. All right. So the first thing that is a prerequisite to solve this problem. So there is a prerequisite. So the prerequisite to solve this problem is the knowledge of a permutation graph. So permutation graph of a permutation. Right. So you simply need to know how a permutation graph looks like for a permutation. So a permutation graph is nothing but the graph which we get if we add an edge between I and AI for all I, where A is the permutation. Let's call it P. So if we add an edge between I and Pi in a permutation, then we will get a graph which will have exactly n edges and also n nodes, right? So the knowledge that we need to have for this graph is that this graph is nothing but a collection of cycles. It's a collection of simple cycles, simple disjoint cycles. So this is what this graph is. So what I'm trying to say is that if you add edges between I and pi in a graph, what you'll get is in a permutation, what you'll get is you'll get a graph like this. There will be some cycles. So let's say this is a cycle, then you will get this cycle, then maybe pi is equal to I, so you will get a self loop, or maybe pi equal to pj and pj equal to pi, so you will get a loop like this. Right. So sorry, pi equal to pj and pj equal to I. So in that case, you will get a loop like this. Right. So this is how the graph will look like. It will be a collection of cycles. Okay. Cool. And now you need to notice what happens when you swap two elements, or what happens when you put an element to its correct location. Okay. So for that, I'll take a simple example. I'll take an example of a graph which looks like this. So there is one, there is two. So we have one, two, three, 4, and 5. A simple graph like that. So this graph corresponds to a permutation, and that permutation is nothing but, so if there is an edge from 1 to 2, that means A1 is equal to 2. Similarly, A2 is equal to 3, 4, 5, and 1. So this is the permutation to which this graph corresponds to. Now, what you need to realize is you need to realize what happens when you swap and put an element to its correct location. So let's say we swap 1 and 2, and in that one operation, we will put 1 to its correct location, right? So this permutation will then be transformed to something like this. So we'll have 1, 3, 4, 5, and 2. So now if you add edges between I and AI, the graph that you'll get is you'll have an edge between 1 and 1. So that will be a self loop. And then you'll simply have this. So there is 3, 4, 5, and 2. And then A2 is equal to 3, so you get a cycle, right? So yeah, this is how the graph is looking like. So notice what happened between these two versions of the graph. So once you put 1 to its correct position, essentially you have just removed 1 and you have added an edge here, right? So this is what has happened virtually. Although, as you can see, there is an edge between 3, 4, 5, and 2. So essentially, you have added an edge between 2 and 5, and that is what has happened here. So this is the edge I'm talking about. So essentially, you just removed this node from the graph and you joined these two nodes, right? So you remove this and then you join this. So this is what an operation does in which you put one element to its correct location. So in one cycle, how many operations will be required to send all the elements to their correct locations? So in a cycle of size S, we will need exactly s minus 1 operations to put every element in its correct position in the array. That is ai is equal to I. To make ai is equal to I. Notice that right now I'm just solving the problem of sorting the array. I'm not taking into consideration that we need one inversion. So I'll just add that thing later. It's really a very simple thing that you need to do. Okay. So what I'm trying to say is that for each cycle in the permutation, just give me a moment. So for each cycle in the permutation, what we'll do is we'll just use that cycle, and if that cycle has a size of s, then we'll perform s minus 1 operations, and all the elements in that cycle will be put in their correct positions. The reason for this being s minus 1 is that if we just do 4 operations here, then we'll be left with all these 5 elements forming a self loop. So if we have this and then we remove 3, so we'll get a graph like this: 2, 4, 5, right? And then we'll remove 4, we'll get 2, 5. And once we remove 2, we'll get 2 and 5 separately. So in total, we apply 4 operations to get this, right? Cool. So for a general permutation having C cycles, the number of operations which we need to sort that permutation would be n minus C, where C is the number of cycles. Okay, cool. Now let's come to our original problem and realize what happens when we need when we need exactly one inversion, right? So exactly one inversion just means that ai is equal to I for every I except two consecutive numbers. So that is the permutation. So that is the permutation that we need, right? Now notice that this is a claim, and let's try to prove it. So what we know is that in a sorted array there are no inversions, right? And if we need one inversion, we'll just have to swap two adjacent elements from the array, right? So for example, an array with one inversion might look like this: 1, 2, 3, 4, 6, 5, 7, 8, 9, something like this. So we just have two elements I and I plus 1 which are swapped, and rest all the elements are at their correct positions, right? So what happens when you draw the graph of this permutation? So the graph of this permutation is really easy. All the elements which are at their correct positions will have a self loop like this. So one will have a self loop with itself, same for two, so on and so forth. But there will be a cycle like this, right? So this is how the permutation graph will look like for a permutation with exactly one inversion. So the only difference here is that instead of having all elements in a self loop, we'll just have one cycle, and we'll reduce the size of that cycle to 2. It's instead of reducing the size to 1. Okay. So that means that we can just subtract the 1 from here and we'll get that. Okay. But notice that okay, I won't write it down straightforward. So what I'm trying to say is that if for any I and I minus 1 are in the same cycle, then instead of reducing the size of that cycle to 1, we can just keep the size of that cycle to 2, and rest all the cycles are reduced to 1. So in that case, the answer is going to be n minus c minus 1. Okay. But if there are no elements I and I minus 1 which are in the same cycle, then what we'll do is we'll have to reduce every cycle to 1, and then we'll have to join some number I with I plus 1 separately in an extra operation. Right. So in that case, reduce all cycles to 1, then join I and I plus 1 for any I. So the number of operation that takes is n minus c plus 1. Okay. So this is the concept. So you just have to find the number of cycles in the permutation, and if there is a pair I and I minus 1 which are in the same cycle or in the same connected component in the graph, then the answer is going to be n minus c minus 1. Otherwise, it's going to be n minus c plus 1. Okay. So yeah, this is more or less the solution of this problem. Let's have a look at the code. Okay. All right, so the code is pretty simple. First, we check if the array is initially sorted. So if the array is sorted, then we just say that the answer is 1. So we can just swap any two adjacent elements and the answer will be 1. Otherwise, we just do a simple DFS. I have done it iteratively. You can do it recursively. We do a DFS and we try to find out the component in which every or the cycle in which every element is. This is all this loop is doing. And C is the number of cycles. So initially I initialize the answer as n minus C plus 1. But if I find out that there is an index I such that I and I minus 1 are in the same component, then I just reduce my answer by 2 and break out. Okay. So yeah, this is the solution to problem D. Cool. Now let's discuss problem E, which is going to be the last problem for today. Okay. So yet again, we have a permutation this time of length 3n. And what we need to do is we are allowed to do two types of operation. In type 1 operation, we sort the first 2n elements of the array in increasing order. And in the second type of operation, we choose the last 2n elements and sort it in increasing order. Okay. And our task is to sort this permutation as always. But to make things interesting, we are defining a function f of p. Here p is a permutation as the minimum number of operations required to sort an permutation p. And what we actually need to do is, given the number n, we need to find the sum of f of p over all the 3n factorial permutations p of size 3n which exist. Okay, so we have n, and there will be 3n factorial permutations of size 3n, and we need to find out sum of f of p over all those permutations. Okay, cool. So let's look at the solution. Okay, we are at problem E. So as always in counting problems like these, we don't really have to iterate on all the permutations and then find out their counts. Instead, a better thing would be to iterate on the counts and then find out the number of permutations with that particular count. Okay, cool. So first we'll do an interesting observation, and that observation is that the total number of operations for any permutation will never exceed 3. Okay, this is my claim. Cool. So why is it true? Why is the total number of operations never exceeding 3? So let's try to briefly see, although it should be pretty intuitive. So we have a permutation of size 3n. So let's divide it into three segments of length n each. Okay. Now there are some elements here, some elements here, some elements here. So let's call this region R1, this region R2, and this region R3. And what I'm claiming is that if you apply an operation of type 1, then an operation of type 2, and then an operation of type 1 again, then we always get a sorted permutation. And let's try to reason things up here, right? So let's look at any element in 1 to n, okay? So any element in 1 to n, it finally should be in R1, right? So let's take all the three cases, whether it is initially in R1, R2, or R3. So if it is initially in R1, then after applying T1, it will still be in R1. And after applying T2, it will still be in R1, and same for the last T1 operation, right? And now let's see if it is in R2. So this is good. So if an element is in R2, then first we apply an operation of type T1. So with this operation, this will come in R1. And once it is in R1, it will always stay in R1, right? Cool. And now let's see what happens when it is in R3. Okay, so if an element from 1 to n is in R3 and we apply an operation of type 1, then it will go to, it will stay the same, right? Because we are not impacting it at all. And then we apply an operation of type 2. So in type 2 operation, we cover this range. So this will now go to R2. And then we apply an operation of type 1, which will again send it to R1. Right. So we have considered all the three cases for a number belonging to this region, and we are sure that this region's numbers will always be in their correct positions after the array is after we do the operation three times. Right. And although I have just proved that they will be in the correct regions, you can very easily verify that they will actually be in their correct positions because this particular operation is simply sorting these elements, right? So their positions will also be taken care of. Cool. So I have done this analysis for numbers from 1 to n, but you can do the same thing for all the other numbers and you'll realize that all of them are in their correct positions. Okay. So yeah, so this is the main concept. We have realized that f of p will be smaller than or equal to 3. F of p is smaller than or equal to 3. Okay, cool. Okay, so now let's look at how we'll solve this problem. So for all I from 0 to 3, what we'll do is we'll try to find g of I. We will find, or let's say we'll try to find capital P of I, which is the number of permutations having f of p is equal to I. So the number of permutations having the number of permutations p having f of p is equal to I. So yeah, if we find out this for all I from 0 to 3, then we are done. We'll simply add I into p of I for all I from 0 to 3 to our answer, and we are done, right? Another interesting thing is that we know that the total number of permutations is equal to 3n factorial. So what we'll do is, so we'll find p of 0, p of 1, and p of 2. We won't find p of 3 because the total is 3n factorial. So we'll just subtract from 3n factorial p0, p1, and p2, and that will be equal to p3, right? Cool. So let's do case by case analysis and let's focus on p0. So in case 1, we'll try to find p0. Now p0 is simple. So if we don't need to do any operation, then that means that the permutation is already sorted. So there is just one sorted permutation. So p0 is equal to 1 for sure. Cool. Now let's look at case 2. So in case 2, what happens is that we need exactly one operation to sort the array, right? So the operation that we'll perform will either be of type 1 or type 2, right? So again, let's see what happens. So we have these three regions in the array and we need to sort the array finally, right? Uh, and now we are applying only one operation. Let's say we apply only type 1 operation and the array gets sorted. What that means is that all the elements from 1 to 2n are in this region from R1 union R2, right? All the elements from 1 to 2n are here, and all the elements from 2n plus 1 to 3n are in this region R3, and they are already in their corresponding positions. So 2n plus 1 is here, 2n plus 1 to 3n. Right, so they are already in their correct positions and all of them form a permutation in the region R1 union R2. So the number of ways for this to happen is nothing but 2n factorial. So this is the number of operations if we are applying T1. But it is also possible that we apply T2, right? In that case, it will simply be reversed. And what we'll have is we'll have that the region from R2 union R3 will have numbers from n plus 1 to 3n. And all the numbers from 1 to n will be present in a sorted fashion in R1. So again, the number of ways would be 2n, 2n factorial. But there is another thing. What can happen is that there can be overlap. So there can be permutations which satisfy the first condition as well as the second condition. That is that all the elements from 1 to n are present in a sorted fashion in R1, and also all the elements from 2n plus 1 to 3n are present in a sorted fashion in R3. And all the other elements are distributed arbitrarily in the region R2. So there are n elements and they are distributed randomly. So the number of such permutations is going to be n factorial, and we are going to subtract this. So the total number of ways is 2 into 2n factorial minus n factorial. Notice that this also contains the sorted permutation. So we subtract 1 from it, right? So final answer is going to be this thing minus 1. So this is going to be P of 1, right? Okay. Now let's look at case 3, which is P of 2. And once we are done with P of 2, we can simply find P of 3 by subtracting from 3n factorial. So we try to find P of 2. So in P of 2, what we are doing is we are essentially doing two operations, right? And obviously, if we are doing two operations, it will either be T1, T2 or T2, T1. So same as before, as we analyzed case one, we'll try to first find the number of permutations which get sorted by doing this sequence of operations. Then we find the number of permutations which get sorted by doing this sequence of operations. But they will again be overcounting. So we'll find permutations which get sorted by applying any either of these two operations, sequence of operations, right? And we'll subtract it. Cool. So let's try to find out the number of permutations which get sorted when we first do T1, then do T2. So T2, T1 and T1, T2 are symmetrical. So the number of permutations will be the same. So we can multiply that by 2. Okay. So we need the number of permutations which get sorted by first applying an operation from T1 and then applying an operation from T2. So again, let's see what happens. Okay. Okay, so essentially what's happening here is that we are applying an operation from T1 and we are applying an operation from T2. So let's look at any number from 1 to n. So if we look at any number in the range from 1 to n, it should definitely be present in R1 union R2. The reason is that once we apply T1, we need to make sure that that element goes to R1, right? So it should be present in R1 union R2. And if we do that, then once we apply T2, then the array will be sorted. So all we need to do is to make sure that all the elements from 1 to n are present in the region R1 union R2. And the size of this region is 2n. So we can choose any n positions in these 2n positions R1 union R2. So C of 2n comma n. And then we can distribute these elements in the n factorial ways. And all the rest of the elements can be distributed in 2n factorial ways. So 2n factorial, right? So this is the requirement because once we perform T1, all the elements from 1 to n will go to R1 and all the other elements will go to R2. So we'll just have to perform T2 again and the array will be sorted, right? Now the same goes for the sequence of operations T2 comma T1. So what we'll do is we'll multiply this by 2. And now we'll have to just subtract the permutations which satisfy both of these sequences. Okay. So those elements are such that all the elements from 1 to n are in R1 union R2 and all elements from 2n plus 1 to 3n are in R2 union R3. Okay. Now this is one thing that cannot be found in constant time, at least not by me. Or maybe there is some binomial reductions that we can do. But what we can do here is that notice that R2 is a common region in both of these terms, right? So what we can do is we can iterate on the number of elements in 1 to n which are there in R1. So we will iterate on the number of elements in 1 to n which are put in R2, right? So let's say we put I elements from 1 to n in R2. Okay. So we have again we have R1, R2, R3. So I out of these n positions are filled with elements from 1 to n. And since we want all the elements from 1 to n to be in R1 union R2, n minus I of them would be here, right? Okay. And now we want all the elements from 2n plus 1 to 3n to be in R2 union R3, right? And what is the size of R2 union R3? It is 2n minus I. So in these 2n minus I, there are these n elements in the range from 2n plus 1 to 3n. So the final expression that we get is first we'll select I elements in R2. So the number of ways to do that would be Ci comma n, right? And then we'll select n minus I elements in R1. So the number of ways to do that will be you select n minus I elements in Okay, so there is a better way to do that. Yeah. So one thing that you can do is that I think this also will work fine. So first you select I elements in R2 where you will be putting so CNI, you will be putting elements from 1 to n. And then there is R1. So the size of R1 is n, and you select n minus I elements from there, right? And then in the next, here there are another 2n minus I elements. So in those 2n minus I elements, you will be selecting n elements, right? These are elements in the range from 2n plus 1 to 3n. So now you have placed all the n elements from 1 to n and the n elements from 2n plus 1 to 3n. So the rest of the n elements can be placed arbitrarily. There are n factorial ways of placing elements from 1 to n, another n factorial for 2n plus 1 to 3n, and another n factorial for uh, n plus 1 to 2n, right? So this is the final expression that you get if you have I as the number of elements from 1 to n which occur in R2. So you can simply iterate on that and you'll get the final answer. Keep in mind that this final summation, that is this expression, subtracted with the summation over all I of this expression. This also contains the permutations who have their p-value equal to 0, 1 and 0 and 1. So you also need to subtract them. And then you can finally subtract it from 3n factorial to get p of 3. Okay. So yeah, this is the final solution. Let's just have a look at the code. Okay, so what I'm doing is I'm having this f function, f of 0 equal to 1, f of 1 is equal to the expression which I already described. Same goes for f of 2. First I'm finding it out without subtracting the overlapping cases, and then I'm having this variable sub which denotes the number of overlaps. And this is the same formula that I used there. I'm using this formula and I'm trying to find out f of 2. I'm subtracting from f of 2, f of 1 and 1. And then I'm subtracting from 3n factorial f0, f1 and f2 to get f of 3. Finally, for all I from 0 to 3, I simply add I into f of I to my answer, right? Okay, cool. So yeah, this is all that I had in mind. Hope this was clear enough for you guys. And thank you for watching. I'll see you in the next one.